Hello everyone, I'm Akshit Jindal and in this video I'll talk about a work, Army of Thieves, enhancing black box model extraction via ensemble-based sample selection. I'll start with a crash course on what is a model extraction attack. Machine learning has become an ubiquitous tool nowadays, allowing individuals and businesses to harness the power of data for informed decision making. To turn these insights into revenue, deploying machine learning models through machine learning as a service has become the go-to with accessible solutions allowing for easy monetization. However, this API access is all an attacker needs to steal your model and or at least create a good enough duplicate copy of it. Such attacks are called model extraction attacks, and these kinds of attacks are a significant threat to your intellectual property, which is your machine learning model. Now, what are the dangers of model extraction? Just by creating a good enough duplicate copy, the attacker is already contributing to intellectual property theft. And if he performs adversarial attacks using that duplicate copy, those attacks will transfer to your original model also. And this adversarial samples can be used to diminish the competitive advantage of your model and at least damage your trust and reputation in the market. So to conclude the crash course, we now know what is a model extraction attack, which is given query access to a classification model. Can we create a functionally equivalent copy of that? Why would an attacker do this is to steal your model's functionality or at least create adversarial examples to bring your reputation down. And how is this performed? In a similar process to knowledge distillation, we query the target model on natural or synthetic samples and we train a duplicate copy using these queried labels. So for our work, what was our motivation? That an attacker would very likely try to minimize the cost of training their own duplicate copy. Existing attack strategies in this area utilize active learning and semi-supervised learning to maximize query efficiency. All of these approaches train a single thief model, relying on which may lead to suboptimal sample selection. And depending on the thief model's learning capacity and which is due to its architecture and the data it was pre-trained on, noisy samples might also creep into the mix. In our work, we train multiple thief models with varying learning capacities and architectures and utilize the wisdom of the crowd to maximize query efficiency. Now, why did we try an ensembling approach? Ensembling has been tried and tested and was the go-to mechanism in machine learning when we needed performance robustness. The bias and variance of an ensemble is typically lower than that of a single model. The diverse representation that each model allows us to capture makes the ensemble more likely to perform better on a variety of data distributions. And the third case is, of course, novelty of application. Ensembling has never been explored in the area of model extraction attacks to the best of our knowledge. Now, moving on to an overview of our approach. First, we have a thief dataset, which is an unlabeled dataset collected from publicly available domains. We select an initial query set or our seed set. We get it labeled through our victim, and we train all of our ensemble members on this labeled subset. We sample these predictions, the ensemble's predictions on the unlabeled dataset, and pass them to our subset selector, which is our active learning module. And this module provides us with the next set of samples to query from the victim. After the query budget has been exhausted, the leftover or remaining unlabeled samples are utilized to improve the accuracy of the ensemble even further through semi-supervised learning. More details to follow. Now for the active learning or the ensemble-based sample selection, the pipeline is pretty straightforward. We collect the ensemble's predictions on each individual unlabeled sample. The softmax vectors are either averaged in the first method, consensus entropy, or used to compute a disagreement vector based on each label's frequency in the prediction set. The entropy of these two vectors serves as the uncertainty measure for sample selection. We use the core set or k-center approach on top of this to push the boundaries of selection efficiency. Moving on to the semi-supervised learning approach, we adapt the fixed match method proposed by Google to an ensemble setting. Each unlabeled sample is first weakly augmented and both the original image and the weakly augmented image are queried from our trained ensemble. The top one predictions with the respective confidence values are stored and are used to compute the number of label changes between the original image predictions and the weakly augmented image prediction. If the number of label changes is less than or equal to 1, we say that our model is quite confident regarding this particular image. And if the confidence values are further greater than 0.9, which is a confidence threshold, we select this image as a part of the semi-supervised learning training dataset. We perform strong augmentations on this and use this strongly augmented image to train the ensemble even further. This leads to a great boost in extraction accuracy. When we sample our ensemble approach, we outperform every previous approach on the data sets that have been used to demonstrate the extraction accuracies in the previous literature. You can go through the paper for a detailed analysis of these results. The K-center selection refinement provides a significant boost for higher dimensional datasets. But the same increase is not observed for low dimensional datasets like CIFAR 10 and CIFAR 100. Furthermore, performing adversarial attacks on one of our ensemble members, whose architecture was kept same as the victim model, leads to superior adversarial sample transfer, an increase of approximately 21% over previous work. The victim's accuracy drops considerably even when the victim and the thief model architectures do not match, as is demonstrated by the dense-net architecture over here. These are the training curves for the active learning process. We have reported accuracy numbers for each cycle for each ensemble member. For the consensus entropy method, where we average the softmax vectors of each member, the accuracy improves smoothly for high dimensional datasets, but on the small dimensional datasets, there is a slight inconsistency in each cycle's accuracy. We are still not aware of why this is happening, and we wish to explore the reasons behind this in our future work. A similar trend is not observed in the label disagreement method, where the weak learners play less of a role in sample selection. So to conclude our presentation, our method, Army of Thieves, performs better than previous methods in terms of extracted accuracy and query efficiency. We focus on image classification tasks in this work, but our ensemble approach is generic enough to be applied to any domain, like speech, text, etc. We just need to adapt the corresponding active learning and semi-supervised learning approaches. The selection of ensemble members can be streamlined by an effective metric that quantifies the information capturing ability of the architecture for the given task. This is a very interesting future work direction, and we leave this task for future work. We also invite other researchers to work in this direction. That's all, and I would like to conclude my presentation. Thank you for listening.